Good afternoon, everybody. Yes, my name's Neil Reynolds. I'm as Nick said and I said, I'm a senior research fellow in the Warwick Manufacturing Group. A very brief introduction to the group. So this project is being carried out within the Materials and Manufacturing Directorate within WMG. It's headed up by Prof. Tom Pies, who joined us just over 18 months ago, and he's heading up the National Polymer Processing Centre initiative. So within the MPPC, there's a portfolio of projects being established across the TRL MRL range from EPSRC through Catapult and up to Innovate UK towards exploitation. And we're looking at sustainable polymer solutions for sort of very high volumes, so things like polymer packaging, but also relevant today, low emission mobility, so structural lightweighting, metal replacement type materials. Next slide, please. So Vario-thermal tooling, it's an area that we've done some previous research in, and it refers to tooling that we can rapidly vary the surface temperature of the tool using various means. And the point of this project is to determine if we can use thermoelectric modules to do the same thing. So basically, it's a Peltier module. The reason we're interested in the Vario-thermal tooling is it allows us to very rapidly vary the surface temperature of a tool, so we can basically melt process thermoplastic polymers isothermally prior to then cooling them in a controlled way. The advantage of that is we can get to very short cycle times while still maintaining an isothermal process window. So the advantages of a thermoelectric module would be that the actual heating and cooling element is in direct contact with the tooling elements. That's the tooling surface. So there's a thermal couple, and we can use the thermoelectric module to manage the heat flow. So we can actually store and reuse heat energy between cycles. So quite a lot. There's existing technology that uses fluid coupling for the same thing, so air and liquids to move and to heat tooling surfaces. But the idea here is to actually move the heat around in the tooling system. So the key research areas are firstly an evaluation of the suitability of the Peltier technology in terms of things like heating, cooling rates, and the maximum temperature. Looking at things like the process energy requirements, and then how we actually control the system. And of course, there's some scientific objectives as well to see what the resultant properties of the material are. Next slide, please. So very quickly, on the right hand side, you can see a typical process breakdown for this variothermal process, where we have three key stages. We have a preheat stage on the left, a melt process stage, and a rapid cool. And looking at the schematic graph, we have temperature versus time. You can see there's a rapid increase in temperature, a hold during the melt process, and then a rapid cool. Looking at the left-hand diagram, where you can see the different tooling elements, you have the upper tool surface, which is 2 to 3 millimeters thick, the active Peltier element in the middle, and then a heat sink behind that. And that's what I was saying about you can effectively move the heat around within that system to process the material. Next slide, please. So an example of a Peltier shown on the right. It's typically 40 by 40 millimeters square. The approach we're taking is to try the technology on a 1D scale, as we're calling it, so a single module, to generate effectively formulate our control and measurement strategies, and doing some parametric studies, and then very quickly moving on to a 2D system where we've got an array of modules working to globally and locally vary the temperature of the tool surface. You can see hopefully the video on the right shows that kind of assembly. And that will allow the end goal of the project is to do some flat to flat level trials and demonstration to see how the technology actually works. One thing to note is that we are using off-the-shelf modules which are actually built for cooling and energy harvesting applications. So regarding the robustness and the sort of heating and cooling speed, they are not necessarily built for this purpose, and so we are partnering with European Thermodynamics within this feasibility study and discussing how we could actually make bespoke modules for this application. Next slide, please. So the first part of the work we completed is 1D study on a single module. You can see the stack in the bottom left picture. You've got the tool surface and the Peltier module in the middle, and then the heatsink behind it. We've done this. The data shown here is an example cycle for a polyamide 6 process with no material, just the tool surface. So we're going from 240 degrees down to 170 and then back up. So the middle graph shows temperature versus time at the tool surface and the rear plate, and you can see that we can get down to and back up again in about 100 seconds, which is very encouraging. It's faster than the existing variothermal technology we've been evaluating. On the right hand side, that shows us the actual cooling and heating rates. So in blue, the cooling rate shown on the right hand side of the right hand graph, going down to about minus 3.5 degrees a second. The efficiency drops as the temperature differential drops. It goes down to about 1 degree a second cooling and heating. But the sort of take-home message from this is we can do as I said, the whole cycle in about 100 seconds. So if you were to include a dwell in there, you could probably do the whole thing in about 3 minutes. Next slide. So we're now in the middle of the 2D coupon study. You can see the apparatus on the right-hand side. It's a 2x2 array of Peltier modules. We're looking at polypropylene and polyamide 6 UD tape laminates. So they're going in dry, and then we're doing the full consolidation under a vacuum bag. And we're measuring the temperature at the tool and inside the material and establishing key criteria such as maximum minimum cooling rates and as discussed, the actual characteristics of the modules themselves. Could you move to the next slide, please? So these are the results from the actual coupon testing. So if you look at the graph on the right, you can see in orange the temperature versus time for the tool surface, and then in blue the mid plane of the 2 millimeter thick laminate. And you can see that I've divided the graph into 3, so you can see the heat, processing, cool stages. There's about just under 60 seconds dwell in the middle, and we arrived at this cycle time based on visual inspection of the laminate. So basically trying to manufacture a fully consolidated laminate. The parameters that we've used are translated into a total process time of about 400 seconds, so 6.5–7 minutes. So certainly under 8 minutes we can do a full heat cool cycle on a single-sided heating system. And that the bottom right graph shows us that heating cooling rate we achieve at the tool surface and in the material. Because the materials are a relatively good insulator, actually in the mid plane of the material we're only seeing heating and cooling rates of about 1 degree a second. What's interesting about this, on the right hand side of in the cooling stage, in the top graph, you can see hopefully a little bump, which is actually the crystallization exotherm that occurs during cooling of the polypropylene. And we think this is quite interesting. So if we move to the next slide, we've done the same analysis on the polyamide material, semi-crystalline material, and you can see the data from a cooling stage on the right hand side, where we've got in green temperature versus time, but the black line shows the actual cooling rate versus time, and effectively the cooling slows down during that crystallization stage, and you can effectively see the onset, peak and end of crystallization. And replotting that data, as you can see in the bottom right hand side, you can actually see it's almost like a DSC trace for those who are familiar, where you're actually plotting temperature versus cooling and heating rate, reading from right to left. So as the material cools, you can see the onset temperature, the peak temperature crystallization for that particular cooling rate, and then at the end of crystallization, of which you could demold the material. So we're in the middle of doing these parametric heating cooling trials for these materials, and the next stage is going to be to take the resultant material and do some microstructural and DSC measurements on that material. Move to the next slide, please. So this is on the right hand side, you can see our outline design. We're actually looking at for the prototype for this system, we're looking at a two-sided system, which would probably give us much better heating and cooling rates and more industrially relevant, because we're seeing a lot of thermal losses, as you'd expect from single-sided tooling. So that's the design that we're currently working on at the moment and starting to create a bill of materials. But the ultimate conclusions are that we've developed this 1D and small 2D systems that have shown certainly sub-8 minute cycle times for a 2 millimeter thick structural laminate, which is very encouraging. It shows that the technology might have an interest, and of course there's this potential control of crystallinity that we could do, you effectively measuring the onset and peak crystallization during process. So there could be some real-time control aspects introduced into this system that we think is of interest.